Hello, class. This is Mr. Hart. And in this podcast, we're going to begin our unit on pressure and fluids. Okay? And to get started, I want to present a very important question to you. Okay? I want you to think about why is the fact that ice floats so important to life on Earth? Okay? Now, this may seem more like a biology question than a physics question, but we'll see that this has great import to our subject. Okay, but think about this. Why does it matter that ice floats? Water is a very strange substance because it's one of the only things where when it freezes, it actually gets less dense. Most things, when liquids become solids, they become more dense and sink. But water actually becomes less dense and actually floats when it becomes ice. Now, when you get into chemistry, you'll learn why that is, how it crystallizes and makes these hydrogen bonds and all this stuff. But the important thing here is that water is less dense in solid form. Ice is less dense, which is why it floats. Okay, and this is very important because if ice didn't float, okay, there's lots of regions of the Earth that couldn't exist, like all of the North Pole area. It's important that ice floats because if ice sunk, then the water would just get colder and colder and colder because the ice would build up lower and lower and lower. Okay. It caused a lot of ecological problems, to say the least. So, the key here, okay, moving on to the physics side, is water floats because it's less dense. So we have to have a good understanding of density. So density, mathematically, is described, okay, we use the variable rho to represent it, but it's described as mass over volume. So the Greek letter is rho. It looks like a little p, okay, but that actually is rho, okay. It's equal to mass over volume, okay. And if you want easy way to remember that, one way I've always remembered, because my last name is Hart, is that the density is equal to a heart. Okay, you just draw a heart, and then you draw a line through it, and then you get mass over volume. Okay. So that's just a silly way to remember it if you ever get stuck. Okay? But how much stuff we have over how much space it takes up, okay? The units for that will be kilograms over meters cubed, okay? Just simply from the fact that mass is in kilograms, volumes in meters cubed, okay? So it's pretty simple to calculate. Let's just try really quick to make sure we got it, okay? What is the density of an object with a mass of 300 kilograms and a volume of 5 meters cubed, okay? Well, you just say rho equals mass over volume, which in this case is 300 kilograms, and it's over 5 cubic meters, which will give you 60 kilograms per meter cubed. Okay, so it's relatively straightforward, okay, to work with densities. So let's get into a little bit more with vocabulary before we solve this problem. Okay, a fluid, which we'll talk a lot about in this unit, is a gas or liquid substance. So fluid's kind of the joint term meaning either a gas or a liquid. Okay, both of these have properties that we have interest in. And then density is the amount of mass in a given volume, okay, as we've already stated. So another term that's of real interest to us is what we call buoyancy, okay? And buoyancy is the ability of a fluid to apply a force. Now, you probably think of buoyancy as an object being able to float, which it sometimes can, but there's a buoyant force regardless if the object floats or not. Okay, so buoyancy is this ability of a fluid to apply a force to an object. Okay, so when you jump in the swimming pool, the reason your body doesn't sink to the bottom is because there's a buoyant force pushing you up. To start thinking about density and buoyancy and how they're connected, okay, I want to pull up a simulation for you. All right, so here's a simulation that's going to help us think about some things with buoyancy, okay? Now, if I throw a block of wood in the water, you probably know that wood floats, okay? It has a density of 2 kilograms per every 5 liters, okay, according to the simulation, or 0.4 kilograms per liter. As we've already stated, ice floats, so we can make this ice, throw that in, and slowly but surely it will also float. Okay. Hopefully you know things like bricks sink. Okay, its density is 2 kilograms per liter. And hopefully you know that aluminum also sinks, metals and things like that. So the key idea I want you to understand is notice when things go from floating to sinking. So if I make a new block that I just call mine, it's going to have the same properties of ice. Okay, it will just barely be floating, right? And that's at 0.29 or 0.92 kilograms per liter. So if I slowly adjust this to make it more massive, okay, right at 0.99 kilograms per liter, that's when it's still floating. If I make this 1 kilogram per liter, it's barely touching the surface. And if I make it bigger than that, it begins to sink. Okay. So the key here is anything less than or equal to 1 kilogram per liter will float. Anything greater than 1 kilogram per liter will sink. Okay. Now you may think this is just a coincidence that it's at 1 kilogram per liter, but this is how they define the kilogram. It's how much mass water has in a given liter, was 1 kilogram. That's how they initially defined it. So if something's less dense than water, it floats in water. If something is more dense than water, it sinks in water. Okay. So pretty straightforward stuff. So this is hopefully a review. I'm assuming you may have learned this in like an 8th grade science class or maybe even 6th grade. But we're going to get a lot deeper into why this is from a physics perspective, thinking about forces and things like that. But before we get too deep into that, for this lesson, I want to do a little lab. Okay. I want you to think about if the shape of an object affects its buoyancy. And to do that, I want you to complete the buoyancy lab. Okay, it's a home lab. You'll just make a boat out of aluminum foil and put it in your sink and see how many pennies you can fit on that boat. Okay, start thinking about how buoyancy works with systems and objects and stuff like that. And then next time we'll go more into the math of how we calculate this buoyant force that exists. Okay, but hopefully that all made sense. Let me know if you have any questions, and thank you for watching.